All right, guys, we're going to get started again. Okay. Okay. I think it's recording. All right, so I'm going to run the Jupyter notebook here. So let's start building the architecture, okay? So let's get a feel for building this architecture. As I said, we're only building the decoder part. So we're going to start with, we need some data and we're going to process the data in this example. And then we're going to have to create all the layers. And basically, we're trying to build a GPT, okay? So I'm just running the Jupyter notebook that I provided. You can download it and follow along if you'd like. All right. So let's go ahead. So you can read through the ideas, but here, these are the libraries. As you can see, I've tried to make this as consistent as possible with what we've been doing all semester. All right. So the libraries are Torch, NumPy, TorchNN, functional. We've seen all of these. The new one is tick token, which I'm not using in this example, but this is the library that you could use to create subwords or sentence piece or something like that. Instead, I'm just going to take, since it's very small text, I'm trying to make this example as simple as possible, and I think this should work. So run the libraries, basically. Okay. You can install tip token just by doing pip install. Notice it will require probably Python 3.9. Okay, I'm using 3.7 here, so hopefully I won't have any issues. All right, so we talked a little bit about the components of the transformer. So here are some of the ideas. The block size here. So this is the size of a sentence, basically, is 256. So instead of 40, this is 256. Okay? Instead of 40 is 256. The batch size is 64. The max iterations is 5,000, so that's the number of times it trains. There's an eval interval, so every 500 epochs is going to score, give you the loss, etc. The learning rate is this one, which should be 0.0001 or 3. Sorry, that's the learning rate. Notice that this is the command you can use if you have CUDA, a GPU. Then the device is CUDA. Otherwise, use CPU, but it's going to take longer. So you don't need to change anything for this to run on your GPU or your CPU. If you have a GPU with CUDA libraries, it'll work. Otherwise, it'll work on your laptop. Say that again? Yes, CUDA is a proprietary library of NVIDIA GPUs. So like I said, you have to have an NVIDIA GPU to take advantage of this. But otherwise, it'll run on your laptop or PC. It just means it'll take longer. Got it? Eval iterations, 200. The vocab size, notice, is 65. Now, vocab size would usually be 70,000, 100,000, 200,000. But again, I'm only using one script or play from Shakespeare, so it doesn't have that many tokens that are required. And we're actually going to use just the letters in the alphabet as subwords. So in fact, every syllable is of size 1 character, okay? Does this make sense, guys? 65 is the vocab size. Okay. All right. Now embedding, the question that you guys had is 384. Every ID gets embedded to a vector of this size. Okay. Is this clear? The example we talked about with the embeddings, that it discovers furriness, has wheels, that kind of thing. Here we're saying every ID needs to be represented by an embedding of size 384. Okay. Number of heads is 6. Number of layers is 6. The dropout is 0.2. So when it says number of layers, if you go back to this, it means there are 6 of these layers. The repetition of decoder, 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 you do it in a for loop. where you instantiate each of those decoder layers 6 times. One follow, and so you'll have them, and then you'll be able to use. Does that make sense? Okay. Questions? All right. So you've got 6 heads, and you also have 6 heads and 6 layers. Okay. Let's go ahead and hit run. The data is that file that I posted on the GitHub input.txt. The graphs, the figures are also there. So we can just read in that data with this code over here. Is that clear, guys? All right. I want to look at the length of the data. So I'm just going to print the length of text. So that's literally the number of characters in there. So length of data is, what is that number? It's like 1,115,394 characters, basically. Okay. Okay. If I want to print a list of them, I can see them there. These are actually, for this example, this is super tiny Shakespeare GPT, right? This is basically the vocabulary. Okay, I created a set and a list, and it's just these letters and some symbols. Okay. But in real life, we'd have 70,000, 80,000 subwords. And this is where you would use tip token, or you would use sentence piece to get these. Here, we're just doing it kind of manually to keep it simple. All right, then after that, we're going to create the vocabulary size, which is going to be len chars, right? And then we're just going to print it. So you can see there, this is actually the size of my vocabulary is 65, and those are the characters that I'm going to use. So each one of those needs to get an ID, because we can't give letters to a transformer. We need to give it integers, and then the integers get mapped into embeddings. The beauty of that is that NN PyTorch already has an embedding lookup table, is called, which I described to you guys. You can think of it as a 65 by 384 matrix. Does that make sense? That's it. That's your embeddings, a matrix of 65 by 384. Each of the 65 IDs corresponds to one of those rows of 384 that must be learned. And initially, they are just going to be random values. As the transformer learns, those are weights that get updated. Got it? 512. Yeah, I know that in my picture, I have not had time to change that, so I apologize for that. But yeah, you're right. The pictures that I had initially were for 512, which is the original Vaswani paper. That's a good question. But in this code, the embedding is 384. Yes, good observation. Every ID gets embedded to a vector of this size. Thank you. All right. So let's go ahead and keep going. As I said, you guys can play along with this. Then the tokenizer comes in. We need to have a way to tokenize things. So these are called the reverse dictionaries. Is a very common thing in NLP, where you just create dictionaries of IDs to of IDs to tokens, tokens to IDs. Okay, so I'm going to go ahead and do that. And I've created them. Now we can look at them because they're not really that big. And this is why I like doing this example. We had 70,000. This would be impossible to visualize. You can see there, I have a dictionary of letters to integers. And I have basically the reverse of it, which is integers to letters. Why do we do this? Because they're hash tables, and it's just faster to do, compute these that having to from one reverse it and so on. Got it? The speed thing. All right. So now that I've done that, I'm going to create with a lambda function, basically the functions encode and decode. Okay. And these are really nice because basically what they should do is they should take our letters and encode them into integers, and then take the integers and encode them into letters back, right? This is the back and forth that we have to do. So if you notice, this is just regular code, right? This is no neural network is involved here. Notice that I'm going to initialize my encoder, And then I'm just going to test it with the sheep language, right? Right? So that's sheep language. So I'm going to go ahead and run it. And there you go. I got my integers. 40, 39, 46, 46. Got it? That's what you actually plug in into the transformer. If the transformer, the size of an input is what in this one? It is block size 256. That is the maximum. So 40 is 256 here. Okay? Got it? So 40 is 256 here. So you allow even larger sentences, even though you probably don't need them. Anything else gets embedded, gets padded. All right, so now let's define the decoder, again with a lambda function, and we should be able, now I give it the 40, 39, 46, 46, and it should give me back. And there it is. Got it? All right, so this is, I think this should be pretty obvious and clear. All right, so now that we have that, we are going to go ahead and start. Remember that everything that we give into the transformer needs to be tensors. Okay, so I'm going to take my encode function, which gives me, given words, right, or letters, sorry, it gives me the integers, right? I'm going to take it here. I take the whole of the text, which has the whole of the Shakespeare play, right? And I'm going to encode it, and I'm going to encode it into a torch tensor, okay? There it is. That's the whole of it encoded. Does this make sense? So now it's all integers, okay? Now I'm going to split this data because I'm going to have some of it for train, some of it for test, okay? So I'm going to go ahead and do that. And I've created now my train and my validation sets. Now, here you should you should be thinking at this point, but where is the X and the Y's, right? So we always do X and Y. We have an input and an output. In the decoder, if we look at the architecture, we need to have every time an X and a Y, right? An input and an output. What did I say about this when we train? We shift it to the right. So it's the same X as input, which is output, only shifted. Okay? That's what we need to do. Okay, guys? This is what I'm going to try to break out for you guys to visualize. Okay, so here we are. I think I was here, right? So I do this one, that one. All right, so this is now, let me save this. This is the function to create batches, okay? But this actually does a little bit more than that. The sentences are selected for X and Y here, where they are the same, but Y is shifted by 1 from X, okay? So this is what I was saying before. So let's go ahead and think this is just this same function down here, but here I just kind of broke it up into parts so that we can see what's going on, okay? So let's go ahead and run it. So now this is just an example, so it's easier to visualize. So in this example, I have said that the batch size is 4. What does that mean? I'm going to give it 4 sentences at a time. Okay? The block size is, temp block size is 16. So instead of 256, I'm also doing just 16 once again, just so that it's easier to visualize and we can understand really well and remove any mystery as to how we train this transformer, okay? Now, here, this thing here will just predict some random values, okay? So let's go ahead and run this piece of code. You can see that it picked 213,173. It picked 989,153. It picked 193,174 and 874,116. Those are just in data positions that it picked, okay? Starting points, if you will, randomly, 4 of them, okay? So notice that what I'm going to do is now I'm going to pick from data I'm gonna print these four, okay? That's what I'm doing, the four starting points. So I'm gonna do a run, and there they are. Okay, tensors 59, 43, 58, and 17. In the whole of the Shakespeare play that we're reading right now, we're finding these letters, these four letters, and they will be the starting point of our sentence that we're gonna use. So notice it's like we randomly pick things from this Shakespeare text. Okay, everyone with me? Now, this is where the magic happens. Notice that here I'm printing X and Y. What is this X and Y? X is the input to the GPT, Y is the output of it. When we do the training, all the weights need to map from X to Y. Okay, so what we do is we are going for I in IX. You see this? So we start at these IDs, right? The ones that we have here, these big ones here, right? And then we're gonna plug them into data. So we're gonna say I, and then they just go to temp block size. So that what does that mean? It means that we grab, let's say this is 989,000 and the 256 characters following that one in the text, so that we can grab a chunk of the sentence. Yes? Okay. And then now the only trick that you might notice is what? Here we have I, and what do we have here? I plus 1. What is that doing? Effectively, that's the shifting. Okay, that's the shifting. Okay. So let's print it. I think it'll become obvious once I print the X's and the Y's. So I have printed, so I pick the position at the text, 59, and from there, the following 16 letters, which are these. Do you see that? And notice down here, so these are the 4 X's, the batch of 4 by 16. And down here is the corresponding Y batch. And what do you notice here? They're shifted, right? By 1. So this one is 59, 58, 1. This one is 58, 1, 15. It's shifted. I've accomplished my objective. Up here, 39, 52, 42, 52, 42, 1. There's the shifting that I was talking about. That's it. This is the entire trick of GPT. That's it. Okay? This is how you train it. Except that you wouldn't use letters, you would use the subwords, basically, or however they're divided. Any questions? Okay. Yeah, please. Please. Yeah, so think of it in data. No, it's data. So the data of the play goes from 1 to 1,119,000 something. So what this means is we go to position 213,000 in that text, find that letter, and then we grab the additional 16. Effectively, we grab the chunk of that text. Do you guys see what I'm saying? So let me do this maybe. Let me go to the whiteboard. Okay, so here's the whiteboard. And this is the Shakespeare play that we are reading currently. So it starts at 0 and it ends at 250, just to say something. So I picked 4 values additionally randomly. 17, 40, 72, 200. So I start with 17. That's 17. And I grab the additional 16 that follow. So effectively, that's a sentence in that text. That becomes X, and Y is just that same thing shifted by 1. You see how easy that is? Not complicated. Then I pick 40. That's 40. Grab the next 16. And then that's X. And then Y is just that same thing shifted. That's all that's all GPT is doing. It's learning to predict the next word. Okay. Got it? Did I answer your question? Yeah. All right. So now let's go back to the code over here. Okay, so let's say I grab this one, right? Okay, so if I add a new here and I said decode, okay, didn't copy. Let me copy it again. Okay, so I added that basically, right? So air Lucentio something something. You see that? I can grab another one. Truly, sir, I. You see that? I'm just grabbing chunks of the text and I'm feeding it to my tiny GPT, and I'm trying to get it to learn to say things. Is this clear enough, guys? Yeah, please.
Where does this algorithm actually learn micro loss? The decoder or the
Again, so transformers are an encoder and a decoder. So the Vaswani et al. Paper of 2017 was this architecture, done for language translation from one language to another. However, you can break a transformer into the encoder part and the decoder part. GPTs like ChatGPT and all of them are decoder only. So we are only doing decoder in this code here. I'm not actually doing the full encoder decoder with multi-head attention. We're not translating. I just want to generate text that looks like Shakespeare a little bit. So to answer your question, we are only doing this one, the decoder. We are starting, imagine this does not exist, this side. Okay? Yep. So the X goes here and the Y goes here. And we train it like that. Once we have trained it, then we're going to predict. So that means we're going to give it an input. It's going to give us an output, right? And then what do we do with that output? We have to move it down and concatenate it to the original input. And then we give it that. And then, and it keeps predicting. Because you don't want to say, you don't just want to predict the car is going from is and then going. You want to know the car is going. And then the next time around, you want to know the car is going really. And then the next time, you always want to have the full context. That's what the GPT does. Okay. All right. So let's keep going. So we've done all of this. We did that. Okay, I grabbed a chunk of these, and you have seen that they're just basically chunks of the text, right? Shakespeare text. All right, so now all of that I just did to kind of show, but really we have the batch here, okay? And so basically it's the same thing, and it produces X and Y in batches, okay? So it's going to produce, the real batches would be of size 64, so it's 64 by 256 for X and 64 by 256 for Y, where the Y's are shifted by 1. Okay? So that's just the function. So let me go ahead and run that one. So get batch is done. Then after that, we have the standard loss function that we would use. Okay? So we'll come back to that one. Then we have the architecture. This architecture is where we need to build this over here. So we will need an input, right? We will need this. Then we will need 6 decoder layers, followed by a fully connected layer, right? The last one is a final fully connected layer that produces something like that is n by 256 by batch size, which in our case is 65, okay, to predict things. And inside the decoder layers, we have attention layers and normal hidden layers, okay? So that's what we need to do, okay? Build that whole thing. So how do we build that whole thing? We need to explore the pieces for the architecture. So the pieces for the architecture start here, okay? In one head of self-attention. So this is the class for one head. So I have broken this up like this, which is kind of more like the math that's going on, the matrix multiplications. But if you notice, it's commented out, right? So this is just me showing you the computations. And then this is the actual code that we need to use. So I'll come back to this, right? This is a head, which is basically, this is the attention mechanism. The code for attention is happening there, okay? So that's like saying the convolution. So this is probably the last part or the hardest part to understand, okay? The head. But that's basically the self-attention, okay? Another class is the multi-head attention, basically. So I have this diagram actually, which is, this is one decoder layer if we zoom in into it. If you notice, every decoder layer here, one of these decoder layers is basically, if we zoom in, this chart here. So what's important here is you start with a 40 n by 40 by 512, or whatever the embedding size is, and you get an n 40 by 512. Inside we have an attention layer and a fully connected layer. Fully connected layer you guys know about already, because it's what we've been using all semester. X times W plus B equals Y. That's it. But as I said, this multi-head attention is a little bit more tricky. So there's going to be the intuition of how that works, the matrix multiplications of how that works, and the object-oriented implementation of how that works. All right, so we'll look at it in those 3 levels as a last topic, okay? But right now, I'm just doing the overall view of this. Okay, so once again, we start with the attention mechanism. That's this one. Then we have the multi-head attention, which basically, if you notice, there is this line of code. What is that doing? It's creating 6 heads, a list of 6 heads right there. But this is why I kind of broke it up into code like this, so you guys can see the idea. Okay, so we'll need to talk about that. So head is one class that gets used in here. Do you see that? In a for loop, and we create 6 of them, okay? Then we have the feed forward, which is just a standard layer as we've always done, okay? And that's the one that goes at the end. That one, okay? Okay. So we've got head. We got head, right? Then we've got multi-head, which is this one. And then we've got feed forward. Then we have blocks. Okay, so we're going to create all the blocks that we have. So the blocks will bring together multi-head attentions, the feed forward together. Do you see that? And then finally, we put everything together in this class over here, which basically, where does it have blocks? Are these blocks? Do you see that? So the block class, this block class, is instantiated here into a thing called blocks. And that's basically the whole architecture. So this function actually, bigram language model, is the object itself, which you instantiate, and this instantiates everything else that comes in to create the transformer or the decoder. All right, so it's got an init function, a forward function, and it's got our generate function. Okay. So again, I need to drill down into all of this. Now, as you can see, the transformer is way more complicated than everything we've done before, right? Now, take a look. So we got to go slowly through this, but I just want to show you. So bigram brings together everything. And then here, you instantiate bigram to become your model. And that's your GPT right there. So then after that comes the easy part, right? So this is just your optimizer, Torch Optim, as you can see. So that hasn't changed. This is the training process. You grab the batches, you invoke the model, right? You predict things. And then what are these three things? Should be familiar, right? We've been using them all semester. So we zero out the grads, loss.backward, optimizer.step. You see how it starts to fit into our whole process. It's basically the same thing, except that this architecture is gnarly, right? So this is a complicated thing. Once it's trained, you can go ahead and generate, and this is the end of the code, by the way. So then what do we do here? We create an initial tensor, in this case 0 or whatever you want it to be, and you just give it to the function generate of m, where m is your model. And then what does it do? It creates gen text. What is gen text? A sequence of IDs. Those IDs then with the decoder get translated back into the letters to produce the actual text. Everyone with me so far? All right, so now, obviously, the thing that we need to dive into is the architecture, okay? All right, so we've got generate, that's m generate. We've got the training process over here, just like we've done before. We estimate the losses, we grab batches, then we run them through the model, which gives us the values, and then we update the weights. Okay, so we're going to update the weights based on this function, which is our model is over here, model M. So obviously then, bigram language model is what we need to look at. Okay, that's where it all starts. So that's going to be this object over here. Notice, just like before, and it inherits, and then dot module, it's got the init function. Okay, so notice here we're creating everything that we need to do. Okay, we've got this actually is quite nice because really that's that graph that I gave you. It may not seem like it, but it actually is. Okay, so let's break it down into pieces. All right, so these 1, 2, 3, 4, 5 lines of code are actually that picture. I think I'm going to have that picture in just another window, so I don't have to scroll up and down every time I want to. Let me just go to PyTorch, deep learning, transformers, GPTs. That one, right? All right, so that graph is what we need to design, right? The decoder part. Okay, so then now we don't need to do all that. All right, so this is a bigram language model, right? So this is the architecture. Notice that the place where we actually put it together is here. Remember that the way that this usually works is that we initialize things in the init function, and then in the forward function is where we create the sequence of things that we're going to need. So if we look at this decoder, we start with the IDs, n by 40, then that should become n by 40 by 512 or whatever our embedding size is. I think it's 384 in this case. After this layer, right, what do we have? We have 6 blocks, right? And these 6 blocks will have inside the multi-head attentions, okay? Right? And then finally, we have the final layer, and the final output should be n by 40 by vocabulary size, which is 65, because we are trying to predict the next letter in the transformer. Got it? All right. So that's what we look at here. So we have in here, let's just take it one by one. We initialize token embedding table, which is going to be a vocab size by n embedding. So in this case, 65 by 384. So each one of the letters gets an embedding of size 384, right? So we've created that tensor. There is something called the block, the positional encoding. This part I'm just going to skip for now, but just keep in mind, this is what keeps track of the order of the words, so that you know that the car goes, right? So car goes before goes, right? So that's something that gets encoded into the input as well. Then notice here we create an object called blocks, which is a list, an NN sequential, right? We're creating the sequence right there, right? Of blocks. Okay? And we tell it basically how many layers we want here. Okay, so we're going to say how many layers we want, because this is one of the parameters we define, 6 layers. Once we do this, we also need the normalization layer. This is just a norm, right? So we normalize, batch normalization type of thing. And then finally here, notice the final is an NN linear layer. Do you see that? Just like every NN linear we've done before. That's usually sometimes called the head, the something head at the end. But notice what's important here is it's embedding by vocab size. So that's the last part of this. Okay, got it? So we initialize them. Now let's take a look at putting it together. Okay, so we start with IDs and targets are both these batch by the number of tokens, right? So that's basically what we have here. So we token embedding, we take in the IDs, they go into the embedding table and become embeddings of 384. Okay, so that's that step. Then token embedding, we also would go into remember that now we are basically creating the sequence of functions. So then this would go into the positional encoding embedding. As I said, this is what allows you to keep track of the IDs, the order that they appear in. Then these two would become like added together because they have the same dimensions to create X, which is the input. All right, but at this point in the chart, we are here. Okay, we got this one, we got that one, and then now they become an input X. Okay. Then we go in here, and now this is the architecture basically. All right, where we have X going into the blocks. Okay. This X then gets normalized here, and then this X goes into LM head, which is the final one that produces the vocabulary size. So now we have our data going through the entire network, basically. So X goes into the blocks, and then, this sequence of blocks up here, and then that goes into LNF, which is the final value. The LNF is this normalization layer, and then that X goes into LM head. So this is the entire architecture. Just like we did before, where we did convolution 1, convolution 2, convolution 3, final layer, final output. That's the same thing. Any questions? All right, so again, so this is where we capture the whole architecture and we get our final value over here. And then after that, we predict the logits and the loss function. And logits is what actually has the sequence of words. Logits is because you're predicting one hot encoded vectors, right? So you're predicting like out of 65 is this one, out of 65 is this one. So it's usually referred to as logit, but those are the values which need to be converted back into the integers, right? But that's the whole process of the architecture of the transform. Any questions? So the key now is, if you think about it, so when we do this part of blocks, that's actually referring to this section here, blocks, where we've created this thing called NN sequential, made up of 4 in range of n layers. So we created actually 6 blocks. Do you see that? And so these 6 blocks need to have basically a definition, and that's because they're being instantiated here. So then we go into block. Each of those blocks should be a decoder block, right? Do you agree? So what does a decoder block look like? Well, I'm seeing here a multi-head attention followed by feed forward, okay? So each one of those blocks over here, decoder layer, right? Each one of these is that. You see that? And it's made up of the input is a n by 40 by 512, or in our case, n by 256 by 384, right? And it's made up of a multi-head attention and a fully connected layer. The multi-head is the thing that should be new. Everything else is mostly, I would say, like fancy coding, right? But it's the same kind of. Multi-head attention is definitely a new thing. All right, so now we're drilling down in here. So we're going to go to these blocks and let's take a look at what's in here. So what do we have? We have multi-head attention, okay? We have feed forward, which is just a normal, and then we have normalization, right? So we have the same normalization layers. So yeah, so they're just normalizations that are happening every time that we give it the data. Notice we give it X, we run it through a normalization, then we give it X, we run it through a normalization. Do you see that? So you can think of it as every time before it goes into one of these layers, we're normalizing the data. And that has been shown to work. There's a comment here, these normalizations, LN1 and LN2, are about the only thing different from the original Vaswani paper. In the paper, they are done at the end of the forward, but now they are usually done at the beginning of a forward pass, okay? But that's all they are. You can see it's just a layer norm, which I think we've used before, or at least batch normalization. So this has 2 things, if you think about it. Self-SA, which is this one, and self-FF feed forward, basically, which is this one, right? So this just calls feed forward layer, that one. Do you guys see that? And this calls multi-head attention. Multi-head attention is now the hardest thing in this whole thing that we need to understand, okay? So let's just keep it as an abstract thing for now. But what should be important for you guys to see is you get an X, it goes through a batch normalization, goes into self-SA, which is the multi-head attention mechanism, comes out as X, goes into layer LN2, which is another layer norm, goes into feed forward, which goes into X, and that gets returned. Do you agree that that's this? That's that, right? You give it this input, goes into multi-head attention, the output of that goes into fully connected, and it comes out over here. Got it? Now, there's a couple of things that you might wonder in there. Like, okay, why are you, there's X, but it's really X plus this, right? Do you see that? Anyone know what that is? It's a what? No, it's not that. It's a good guess, but not that. This is called the residual. This is extremely important. So remember that there's a thing called the vanishing gradients problem. The vanishing gradients problem was that you had very deep neural networks. So if you do 0.5 times 0.5, 0.25, 0.25 times 0.25, even smaller. 0.05 times 0.05, even smaller. Eventually, what's going to happen to those numbers? They're basically zero, right? If you keep doing that. So that if you keep doing that in a deep neural network, you have a vanishing gradient, which means they become zero or something, and then the neural network just didn't learn anything. This solves that problem. Because you give it X plus a thing, so you're avoiding the zeros becoming super small. Sounds crazy, but that's the trick. And this is called a residual. Got it? All right, so that's, again, it's just one of the things in there. All right, so what have we learned? We've learned that a block, which was instantiated over here as 6 blocks, right? Decoder blocks. Then we drill down into each one of these blocks, and we know that we got an X. This is just, as I said, a normalization, as we've discussed many times before in the semester, that we do the residual, we go through, we need to go into SA. And SA is the multi-head attention. So now, and then also the result of that goes into the feed forward. So we really, I think, just have those 2 things left, or maybe 3 classes left. So let's look at the easiest one. What's the easiest one of those 2? Feed forward, right? Very good. Feed forward, you should know this by now, because it's always W times X plus B equals Y. You know, you can always go back to that. So now we go to feed forward. That's my NN module over there, and it inherits the class. We do the super, we instantiate our class. Now we build our little NN sequential, just like we've done all semester. We have a linear and a ReLU, and then a linear and a dropout. And then we just give it X into this net, and that produces our thing that we want to do. Notice it's N embedding and N embedding. If you say N embedding and N embedding, is that N by 40 by 512, N by 40 by 512? You see what I'm saying? Does this make sense, guys? This is, we're always getting, if we give it an N 40 by 512, an N by 40 by 512, we're getting an N by 40 by 512. Or we're giving it an N by 256 by 384, we're getting an N by 256 by 384. Questions? Sorry?
So we were using X plus feed forward before, so will that change the size?
Let me take a look. Which part? In the here?
X
X
plus.
plus no, because the output, so think, that's a good question, right? So N by 40 by 512 goes in, N by 40 by 512 comes out. X is n by 40 by 512, and what comes out of this is n by 40 by 512. So they both have the same, so they can be added, actually, right? Do you agree? Yeah, think about it. The dimensions that go in here are the dimensions that come out of this one, which is the same as this, so they can be added perfectly nicely. And that's a residual. Yep. Good question. Any other questions, guys? All right. So, yeah, so now feed forward, right? We were looking at that one. As we can see, it's just basically from n embedding to n embedding. Now, what is this one over here? You guys should be able to tell me what this is. What are we doing in the network? We start with 384 and we come out at 384, but in between, we're creating a layer that is 4 times 384. Why? I mean, you know, neural networks, something like that. Right? Do you see what I'm saying? This is just a regular hidden layer. Okay. All right. So now we continue. And now comes like the hard part. Granted, this is difficult. Okay, this is the multi-head attention. Okay, so multi-head attention is this layer over here. So what happens in there is basically that you are going to pay attention to the English sentence that you're giving it. Okay, so as I said, with this one, I'm going to give you the intuition. Then I'm going to give you the code, and then we're going to look at maybe the matrix multiplications as well, okay, of what's going on there. But if you get confused, and 40 by 512 and 40 by 512, but inside there's a whole bunch of multiplications that are happening, okay? All right. So let's go back to our code. So now we need to go into multi-head attention. So I believe, yeah, multi-head attention is this one. Oh, there's one more that calls the actual heads. All right, so yeah, that's a good point. Why do we have heads and then also multi-heads? As it happens, every decoder layer will have 8 heads or 6 heads. I can't remember the number. And what that means is that you will pay attention to your sentence 8 times in 8 different ways. That's why there's a multi-head and then there's just a head. Obviously, the multi-head is made up of heads. So if you guys look up num heads, it was either 6 or 8 in the parameters section. I can't remember exactly. We do the exact same trick we did before, module list nn, where we instantiate 6 or 8 heads. Do you guys see that? So we instantiate 6 or 8 heads. Notice these are actually not sequential. These are parallel, okay? Parallel. What do we have after the heads? An NN linear, just like we've had before. There's a dropout in there, okay? So notice the trick here. Torch cat, right? So that means we concatenate the output of each of these heads in the multi-head list. So here we do 4H in self heads, right? However many heads we have, we iterate and we create basically 6 or 8 heads. We give X to them, and then we get 6 or 8 tensors that get concatenated to create a new tensor. Okay? And then that new tensor then is basically mapped into the next layer, which is the linear layer, to produce our output. We haven't looked at head yet, okay? We haven't looked at head yet. We're only looking at this layer of running X through 6 or 8 heads. So to understand this a little bit better, what I've done is I broke this out into like more linear mathy code, all right? So mathy code, if you will. So I have code here, one of these in red. Yeah, this one. All right, so let's take a look at this one, okay? So that's the same thing, right? That's the decoder layer. Notice what's happening here. I have the C1s are the heads. All right. So I have actually 8 heads in here. Do you guys see that? 8 heads. So if you notice, each one of these multi-head takes in the same input decoder input layer, right? And runs it through that and produces 8. Produces 8. So you basically have like the same, right? Input decoder layer, which is input decoder layer. Do you see that? So the same tensor goes into all these equal heads. They're the same structure, just the weights, hopefully, will be different for each one. That's the idea. Now, you get 8 of them, and then these 8 get concatenated into one single tensor. So obviously, because you want the tensor to be 40 n by 40 by 512, or in our case, n by 256 by 384, we're going to have to know that these cannot be 512. We're going to have to cut them down and divide it by 8, basically. So we get 8 tensors that, when concatenated together, create an n by 40 by 512. You see that? So you might be wondering why that is a thing. And what I can tell you is probably it's like the intuition is like this. The attention mechanism is like the most powerful thing in the transformer. Okay. So what you would want, I'm going to use X just as an input. So you got X, right? You create head 1, which is C1. I'm just going to simplify here, right? C3, C8. Each one of these takes X. They're not feeding from one to the other like we did before. These are in parallel or independent. And they produce these values. Actually, this should have been head, right? So all these should be head. These should be C's. I don't know what. C1, C2, C3, C8. So notice it's the same X going into each one of these, producing C8, which then get concatenated. C1, C2, C3, C8, to produce, in our example, n by 40 by 512. Do you guys see that? But this is n by 40 by 512. If we're just concatenating these, then this cannot be, they're all n by 40, right? You agree with that. So the only dimension that we can kind of mess with is the 512 one, right? So 512 divided by 8 is what? Who can tell me? 512 divided by 8? 79. That doesn't sound. Isn't it 64? 64 or something like that? What's 64, right? So each one of these C's is actually n by 40 by 64. N by 40 by 64. And then you produce 8 of those, then concatenate them to produce n40 by 512. All right, so I'm still back at where I started, right? Why? So there's some ideas here. So I think what they honestly did is this. So they were like, obviously remember that what's happening here is that you're paying attention. So the attention thing is happening inside these heads. That's important, right? They want, before I get into that, let's just think of why they did this part. So a good analogy might be that Lucas looks at some data and pays attention to it in the way he thinks, right? Monica, right? You look at that same X and you think about it in the way that you think. You see that? Then I look at that X and I think about it in the way that I think. Do you see that? So we, the three of us, are heads here. We have an attention mechanism. We get the same X, and we all three thought about it in different ways and produce an n by 40 by 512. Do you see that? Do you produce an n by 40 by 512? C1. Lucas produces an n by 40 by 512. Jacob produces an n by 40 by 512. I produce an n by 40 by 512. Got it? 8 of those. But then, what is 512 times 8? Who can tell me that? 512 by 4096. The GPU then is going to feel that 4096 hit. That matrix multiplication is going to hurt. So what did they do? They were like, that's a good idea to have multiple heads, but we can't take the impact of 4096. So what do? Do a simple matrix multiplication, and instead of producing n by 40 by 512, produce n by 40 by 64. You see what I'm saying? So they still capture the 512, they just project it to 64. And boom, you now have the same thought 8 different ways of looking at the problem with attention, but they shrink the output matrices for GPU purposes. And then they concatenate that to produce a final one that is n by 40 by 512. This assumes then that this output vector has intuitions, you know, because it's constructing a new vector, right? You see how every time you're constructing a new vector, basically, an n by 40 by 512, but it's better now than before. Is that clear, guys? Do you see the intuition of that, of why that was done? We did this, CNNs do this, remember, where we do the convolution and then the max pooling. It shrinks the matrix. We've already established that we can do that. We force the weight, because remember, every time we want to produce something is Wx plus B, right? So we can produce a next layer that has fewer neurons, etc. Okay, so we're done with that. So now, hopefully that made sense. I hope the intuition makes sense. All right, so now that we've explored that, we can go back to our code over here. All right, so that's what happens here. So if you notice, you take the 8 C's, you concatenate them, and then finally, you are at 512, and then you're just going to have one last layer, which takes in, C concat, right? So this is C concat. You see C concat here. What do you always do? Remember, a matmul. Matmul is the actual underlying operation of linear. So whenever you see matmul, it's like looking at that linear, except that in the past, you used to have to code like this. So what you guys just do as linear used to be this, which I prefer. Anyway, so here what are you doing? You take C concat times W times the weights plus the bias, and you get your next thing, whatever it is. And then, what is this one again? Should be the residual, right? Okay, so I think I just noticed it says input decoder layer. Oh yeah, input decoder layer. Yeah, that's correct. Got it? All right, so that takes us then. So hopefully that made sense. Right, that leaves one last thing. The hardest part. We are in multi-head attention. Yep. We did the 8 heads. So that's this part here. Remember, they're all individual. They get concatenated. And then basically you get the output, right? That is n by 40 by 512 or n by 256 by 384. But now we have one last thing to look at. What is actually in head, right? And that's the attention mechanism. So we need to find the class for attention, which should be here somewhere. Yeah, that's the last one. Right. So this is the last part of the architecture where the actual attention mechanism happens. Okay. So this is the attention mechanism includes this idea of keys, values, and key queries and values. Key queries and values. Okay. All right. So this is the code for it. Before we look at, so we can look at this code. I also have code like in the other style and also the intuition of this. All right. So let's start with the intuition, I would say. Okay. So what is the intuition of the attention mechanism? So I'm going to use the example of the book, which has 40, value of 40. Oh, also, here's the sign-in sheet. Can you please sign in? Pass it around. All right, so we have, what is 40 in this context? Number of tokens that we allow, right? Every sentence is initially a vector of size 40. The attention then would be a matrix 40 by 40. Okay, that's the intuition of it. Okay, so let's go to a new here. All right, so I'm going to think of an example. The couple were walking on the bank of the, okay, hold on. The couple walked on the bank of the what? Couple walked on the bank of the river. You see that? Imagine that's 40 tokens, okay? You know, I'm not going to put the padding. Then what do you have? So this is the attention matrix. It's basically a matrix that is 40 by 40. So what do you have on this other side? You also have, I'm going to start by the end because those are really the important ones. So river, the, of, bank, the, on, walked, couple, the. So I was able to fit everything in. You see that? It's a matrix where the goal is to compare the input and itself, right? It's comparing that. But it wants, because at the end of the day, it's trying to create really good embeddings. Do you see what I'm saying? It's trying to produce. It can produce, for the word bank, 2 embeddings. possible, or more. I mean, it could produce more, but let's just think of it producing 2 embeddings. Okay, so here, river and river would have a very high correlation. Let's say 100, right? It's the same word. They always appear together. Same. Couple. How it now you also got to think of how it trains, right? So it's seeing all the novels ever written, all the books ever written, all the newspaper articles ever written. So when it's seeing bank, is it a good assumption to say that it's seeing river a lot? No? Bank and river don't go together? I mean, if somebody is in a bank, they can be in a bank of money, or a bank near a river, or a waterway of some kind. That's where I'm going with this, is that it starts to learn that sometimes when it sees novels, etc., it's seeing bank and river appearing together. So what does it mean? It means that it should pay attention to the combination of these two things. Do you see that? It pays attention to bank and river. And that's important because so you have a neural net, right? You have an embedding or a neural net here. You have the attention mechanism. And thanks to that attention mechanism, you're going to produce another set of neurons, right? So as the data goes in here, it like fires up. Okay, bank and river. Oh, bank and river. What they're talking about is about wet places that have sand and stuff. So then the neural network and the embeddings that get trained fire up around there. Do you see that? That's what intuitively is happening. Another situation, you have the bank got robbed. Oops. The bank got robbed. Okay. And so over here, the bank got robbed. Got 2 B's or 1, not sure. All right. So here then, what's important is it pays attention to the 2 things, robbed and bank. Why is that important? Because once again, it's looking at the word bank as a target. Before we were looking at bank from the context of river. Now we're looking at bank from the context of robbed. 2 different meanings of the word bank. Do you see that? So to look at the analogy before, same neural network architecture, right? This one gets bank and robbed. This one gets bank and river. If we just focus on bank itself, right, we are talking about different things. So here we can say that these neurons represent like more like, you know, sandy, wet places. Whereas now on the other end here produces another set of neurons which have more to do with financial institutions, or, you know, where money is. Still the same word bank. If you think of the embedding for this also, it will be altered. Here, this bank might be all like zeros here where it's like wetness and things like that. And cash, or sorry, let's say this is cash. So here, This would be all zeros, but this would be more like ones or other numbers. And here it's inverted. It's like that and zero. I'm just using an exaggerated example. But my point is, everything in the neural network changes because of this simple paying attention to what I'm saying. This is called it's paying attention to its context. So you'll always hear that the transformer looks at context. It's a context machine because it's not just looking independently at things. It's looking at the fact that I saw the couple walked on the bank of the river. Bank of the river. That's a different thing from the robbers went into the bank and took the money. Two different banks. The embeddings at the beginning are different. The neural network is different. I mean, everything is different in the weights. If we go back to the architecture over here, right? Everything is always going through a multi-head attention to produce this vector. So you get an input vector, but it's being modified over here by the attention mechanism that it's looking at its actual relationship between the words. Does that intuition make sense, guys? Now, I should say it doesn't quite work like this because, in fact, what it does is this idea that we have K and we have Q. If you notice, what is K and Q? It takes in X and it becomes K, and it takes in X and it becomes Q, right? So let's see what key and query are. So they're up here. And what are they? They're just a linear that converts it, right, into some other thing. What operation is that? X times W plus B. And it produces a new thing. But again, those W's have to be learned. You see what I'm saying? Now, why does it do that? Because it gives a little bit more freedom. So it's not really a mapping. The way that I would describe it is a little bit like this. And we'll close with this. And we'll finish up this. We're almost done with the code, actually. So if anything, I'm just going to wrap up. So there might be room for the GANs next week. But you guys, again, so I'll make this before we leave. Everyone's here. Please, next week, everyone needs to present their results on the SciFar 10. I will be grading that, not the report that you submit later. The report you submit later is just for my records, right? And also, got the project the following week. Please do not do that. You can do something as easy as the regressions of the beginning. Just find some data, but you need to implement something on your own with deep learning. It doesn't have to be difficult. You all have to use PyTorch, not TensorFlow or something like that. Okay? Please don't forget this. All right, so to conclude, with this idea of keys and values, the way that I would describe it is like this. You don't actually map, because this would be X to X, right? You guys see that would be X to X? Instead, you do something like this. Imagine this is the attention, okay? So instead of it being X to X, right? They do it, or they designed it, Vaswani and team, designed it a little bit like this. K and Q. Where K and Q are nothing more than, I'm going to ignore the B, and I'm just going to say X times W equal K, and X, well, this is WK, and this is WQ, right, equal Q. So that's how it's done, actually. Do you see that? So you don't compare X to X, per se, which really would be the embeddings of it, right, that get compared. But the X's are not compared directly. Instead, they're compared after the X is multiplied times the set of W's, and the X here is multiplied by another set of W's to produce K and Q, which are the things that are actually compared. that just gives you a little bit more flexibility because those weights can also change and they are trained by the neural net. So I think the intuition there, it's almost like you can almost formulate a question through the weights about that X. And on the other end, you would formulate an answer about that X and find that relationship. That's a stretch. I know I don't have a good analogy, but it gives it a little bit more flexibility. So it's not X to X. It is actually X times some W's and X times another set of W's. And those results, K and Q, are what gets compared. So there's just a little bit more flexibility to adjust those X's and give it more power. Got it? So that's the best intuition I can give you for that. I'll think of a better one, hopefully, for next week. But yeah, we almost completed this. So I'm actually quite happy. I know it's tough code, believe me. But read through it, watch the video again, get the gist of the basic intuitions of it. The code does run. I do recommend that you run it and just maybe give it some Rick and Morty or something, or something fun that you wanted to learn how to speak in that style. All right, guys, please, again, do not forget. I'll stop the video here or actually end it. Please,